My name is Monica Kohler, and I'm a research professor of mechanical and civil engineering at the California Institute of Technology in Pasadena, California. I'm one of the members of the Community Seismic Network research team, and we build and deploy seismic sensors, accelerometers in the free field and in buildings in order to look at their response after earthquakes. My research is in civil engineering, and I'm primarily interested in detecting damage in structures, sort of the way that, say, a doctor might want to detect a break in a bone in your body. And so what I do is I approach that from an experimental and a theoretical point of view. Experimentally, I've worked with a group called the Community Seismic Network, which is a group of faculty members in seismology, civil engineering, and computer science at Caltech. And we've developed the Community Seismic Network, which is an experimental approach to seismic sensing both in the ground and in buildings. So we've built little packages of sensors, accelerometers, that record ground vibrations and vibrations in buildings, and our primary interest is to look at the response of the ground and the structures to earthquakes. So first, we need to put sensors in our structures to record the vibrations, because we never know when the earthquakes are going to happen. So we put them in the buildings and they record vibrations continuously, 24/7, so that when the earthquake occurs, we've recorded the response of the structure or the building to the earthquake. But the trouble is, when the earthquake occurs, we never know if it's going to damage the building or not. So we need to know how the building behaves before the earthquake in order to be able to compare it to how it behaves after the earthquake. So we compare those responses before and after the strong shaking to better predict how the building might respond to a future earthquake, and also to actually record the earthquake. Since we can't predict when the earthquake's going to occur, we have to always be ready for it. We've designed a little sensor package. It's about half a foot by half a foot length and width, and about a half a foot in depth as well. And they're just little plug-in sensors, and so all we have to do is take our sensors, these little packages, to buildings and plug them into Ethernet and plug them into power. So we just use the existing infrastructure in the buildings to plug them in, and once they're plugged in, the software has already loaded. The software just starts running right away, and the recording happens immediately, and then the data are sent in real time through the internet to our archive and our computing systems. One of our long-term partners is NASA JPL, the Jet Propulsion Laboratory in Pasadena, California. And we have over 200 sensors deployed on the JPL campus. About half of them are on the first floor or basements of their structures, and about half of them are on upper floors of buildings. So we hand them the boxes and we show them, where to do the connections. We show them how to point the boxes north, and then plug them in, and then they're ready to go. As long as there are network connections, they're ready to go. Right now, we've only covered the greater Los Angeles area because we're going after density. What we really are interested in is having a high density of recordings, both on the ground and in buildings. And of course, the best way you can do that is to start with a localized area and then just expand from there. So we've deployed most of our sensors in the San Gabriel Valley and the greater Los Angeles area, both in the free field, but also on upper floors of about 10 or 11 high-rise and mid-rise structures. Our blue sky would be to have high density of recordings and high density of stations both in the free field across the whole state of California, if not the entire West Coast, wherever we have a seismically active region, as well as every single floor of mid-rise and high-rise structures. And there in the structures, of course, the goal is to be able to do damage detection after strong earthquakes. You can put these sensors anywhere, in any type of building, anything that you're interested in looking at earthquake response of. So yeah, you could easily put them in homes. In fact, several of us on the Community Seismic Network team have them in our houses, and they're recording the vibration in the house. But we have a lot of our sensors in commercial buildings because we partnered with a company who is interested in looking at the earthquake response of the buildings that they own and manage. We have a theoretical aspect to our research that it complements the experimental part. So in addition to wanting to expand the reach of the network, we're also doing computer modeling of the structures that we've instrumented. And so to do that, we build finite element models of all of the buildings that we've instrumented. And so having the structural drawings given to us by our partners is very helpful in that respect. And so we use these computer models to make predictions for how the building might move in some future scenario earthquake. Plus, it gives us an idea of what the signature data might look like if the building were damaged because of a large, future earthquake. Right now, it's the commercial building owners, or in the case of NASA JPL, it's the facilities engineers who monitor and maintain all of the buildings. But in the future, it would be anybody who is interested in making some decision about what to do in the face of strong shaking. So one of our other big partners is the Los Angeles Unified School District. We have sensors in some of those school campuses, and so there, the principals would be the one who would be interested in having the data products that come out of the network so that they could make decisions about what to do with the teachers and the students on those campuses. One of the most surprising things actually doesn't even have to do with earthquakes. It was just one of those serendipitous moments that happened because we had the network running in a high-rise building. We've recorded several small earthquakes, and they show up very clearly inside the building. But there was also an explosion that occurred about 20 miles from that building, and the explosion sent airwaves through the air, and the building responded to the pressure in the airwaves. And so the same accelerometers that you can use to record earthquakes also recorded the building response to the explosions, because an explosion it's not the same thing as an earthquake, but it has kind of an analogous vibrational response in buildings. So you can get a sense of how the building may have become damaged because of explosions. So this is another big surprise, because we haven't had that many earthquakes, at least not large earthquakes recently. And we have to be prepared for that, but we haven't had a lot of large earthquakes. So we haven't recorded a lot of earthquake data, but we've recorded a lot of other data, including wind gust data. So in Southern California, we have what are called the Santa Ana wind events, which are very large wind gusts that tend to sweep the area from about November through March. And every time there's a large wind event, we see the response of high-rise structures to the large winds. And in fact, we can look at the recordings made on these community seismic network accelerometers and watch the buildings swaying back and forth during the wind event, the same way that they might sway during and after a very large earthquake. So it gives us a sense of whether the sensors are working correctly. I haven't worked directly with CEA. I think that the openness about wanting to gather more information, and that of course would be done best by putting sensors in many more locations, is a really laudable goal. And so I suspect that hopefully there will be a partnership in that we can provide some technology, some badly needed technology, in terms of sensors that could be placed in structures, whether they're homes or apartment buildings or business buildings, in order to collect the data that would be useful in determining what we call microzonation maps, for example, that give a sense of what the amplification due to future earthquakes might look like, as well as doing very rapid post-event response in structures that have instruments in them. Building codes are built based usually on computer modeling of a structure before it's built. And building codes are informed by how buildings respond to earthquakes. But we don't know how they've responded to earthquakes without having sensors and recordings from their responses. And so knowing how a building actually responded to an earthquake, how it shook and how it was damaged or wasn't damaged in earthquakes, helps us, it informs us about whether the code is written correctly or if there need to be modifications to the code for certain types of future events. We're concerned about a lot of types of buildings. Non-ductile concrete is one, soft story structures are another. We initially focused on steel moment frame structures because of the fractures that occurred at beam column connections after the 1994 Northridge earthquake. And the problem with those fractures was they're relatively small, and so they're hard to detect if you didn't have instrumentation in buildings, which most buildings didn't have any instrumentation in them. So the only way to detect whether the fractures occurred is to go look for them, but you don't know where to look for them in many, many buildings. So we instrumented buildings in order to determine what the signatures of fractures in data would look like, so that in the future we would be able to detect that a fracture occurred based on the recordings that the seismic network makes.